Welcome to Flash 101, Pure Storage's educational video blogging series on some of the basics of flash memory and storage and performance measurement in storage environments. My name is Matt Kixmoeller. I'm the VP of Product Management here at Pure Storage. Today we're going to talk about latency. Latency is probably the most important storage performance measurement that you can use in your environment to understand how well a storage array is performing in an application environment. Quite simply, latency is defined as that round-trip time it takes for an application to ask for a piece of storage or to push a piece of data down to the array, and for that array to acknowledge and return that storage request. Now that's a round-trip time, and it includes everything from the request to the actual transfer of the data back and everything in between. So why is latency important? Well, it turns out that each of your I/O transactions of the storage tier is really not independent. There's some sort of application that's driving the storage, and it's asking for multiple I/Os to form some sort of a transaction at the application tier. So think of a database application as an example. There might be a database transaction going on, and there might be several I/Os down at the storage tier required to store or retrieve data to culminate a full transaction. And so one of the important things to realize about I/O is the I/Os are not independent. Oftentimes they're linked in some chain by application logic, and it's the sum total of those I/Os that ultimately impact application latency. So let's dissect latency a little bit and understand the various pieces of that round-trip latency. In the case of a read request, the application requests a read through the SCSI layer, and the first thing that might impact the latency outside the actual storage is actually that transfer time. So people oftentimes think about latency as just how well their storage is performing, but there's a few other things in the chain. So this is one of the reasons that the size of the I/O matters quite a bit. I/Os can vary in size from just a few K to many, many K. And so a very small I/O might go through the network and be transferred very fast compared to a larger I/O. So if you double or triple your I/O size, you can't expect the exact same latency. A higher latency for a bigger I/O might be pretty good, whereas that same latency for a very small I/O might be pretty bad. So the first thing to understand, especially when you're comparing two latency numbers, is how big are the I/Os and are those comparable? The second thing to understand is queue depth. And so every array has a port, as does your initiator, where I/Os can queue up and wait. And so if that I/O is having to wait before it even gets into the storage array, then it's not necessarily a measure of the overall performance of the storage array itself. So the second thing to understand is the latency over the network and potential queuing that could happen at any of the ports in the network. And then the third thing, of course, is the actual response time of the array. The array itself then responds with the data to be transferred back to the host, and a number of things within the array could make that array have higher latency or go slower. Everything from contention on the controller to busyness in the CPU and the architecture on through to the actual disk and waiting for the hard drive to spin and to read the data to return it to the application. So it's really that sum total of that whole transfer time and trip that is that overall latency number. Let's talk a little bit now about average latency versus peak or max latency. This is one of the big areas that I see folks getting confused when thinking about latency, because a lot of what we talk about in industry is average latency. And this comes back to that issue of not all I/Os being independent. So if you look at a traditional storage array, a traditional storage array will start with latency somewhere around the order of 5 milliseconds. And then as the IOPS rate to the array, or the busyness of the array, starts to increase, there'll be a natural decay where the IOPS response, or the latency response time will go from 5 to 10, 15, 20, and you'll have outlying I/Os that are even more. And at that point, the array's performance will generally become untenable. So oftentimes people will want to look at this curve and say, okay, for a given IOPS rate of my application and a given latency I'm trying to hit, what's the maximum performance my array is capable of? And that's a good starting point to understand the performance of a storage array. But hidden within here is the realization or the fact that this is just an average latency. And there turns out to be quite a wide band of actual performance in here, where the average might be 5 milliseconds or 7 milliseconds, but there's a few I/Os that respond faster, and many I/Os that might respond worse, where you could have a max latency of 20, 30, 40 milliseconds. And depending on your application, if an application is stitching together many I/Os, those will have a compounding effect where that entire transaction could take much longer as a result. So there's two important things that are important to understand when you think about latency. Not only what is the average latency, but what is that span, that breadth of minimum to maximum latency and worst case that's being delivered at any IOPS rate. And this is a great place to talk about the benefits of flash. So fundamentally, disk is rotational, and whenever there's a mixed workload, IOs start to queue because they're waiting for that disk to rotate to deliver them, and that's the latency that gets introduced. The great thing about flash memory is it's non-rotational and can deliver very consistent latency. So typical flash arrays deliver latency at around less than 1 millisecond. And as the IOPS load starts to increase, what you want to see out of a storage array is ultimately consistent performance. And that's exactly what flash can deliver. Flat line performance and consistency in that performance through increasing IOPS load. And beyond that, a very tight range of potential performance, where worst case IOPS never exceed a couple milliseconds. So that's one of the real big advantages of flash, not only delivering a great consistent or a great IOP or overall latency number, but a very consistent bounds by which that variability of latency occurs. So hopefully that was a good starting point to understanding latency in your environment. And to recap, understand average latency, understand max and min, and understand how that latency changes over time with varying IOPS load as your application load increases. Thank you very much, and hopefully you'll join us next time for Flash 101 from Pure Storage.